So in this lesson, we're going to explore the binomial expansion. So first, what is the binomial expansion? Well, it's when you take a binomial, such as a plus b, and you raise it to increasing degrees. So it's to the 0 power first, then to the first, and to the second, and then to the third. And there are a ton of patterns in the binomial expansion that we're going to look at. So I first just did the expansion up to the 3 that you should know from this far in Algebra 2. And just writing them out like this, you can start to see some of the patterns. First, notice the patterns in the exponents on a and b. On the third power, it starts off a cubed, then it becomes a squared b, and then ab squared, and then b cubed. And it's most evident in this row here that the exponents on the a start off with that exponent there, the power of the binomial, and then decrease by 1 each time. And as the a's exponent decreases, the b's exponent increases. So a is 3, 2, 1, 0, while b is 0, 1, 2, 3. Right? So with that one pattern, I can figure out, without multiplying anything out, what the picture of the exponents are going to be for the 4th degree of a plus b. So I know it's going to be a to the 4th plus something a cubed b plus something a squared b squared plus something ab cubed plus b to the 4th. Now, this coefficient's also going to be really easy because you notice at the very end it's just the b to the power. So I know this one's 1. The question now becomes, what are these other coefficients going to be? So now what I want to know is there a pattern in the coefficients? So let's pull out the coefficients from the expansion to see if we notice a pattern. Well, the first one is 1, and then I have 1 and 1, and then 1, 2, 1, and then 1, 3, 3, 1. And for some of you, this triangular array of numbers looks familiar. That's because it's called Pascal's triangle. And where do the numbers of Pascal's triangle come from? Well, they come from the top 2 numbers above it. So if I want to know the next number, well, first off, Pascal's triangle, the outer sides of the triangle are just 1. But if I want to find the next number, I can look at this pattern. It goes 1, 2, 3. So the next number is going to be a 4. Now, what about this middle number here? Well, this middle number and every number above it is generated by taking the top 2 numbers directly above it and adding them together. So this 3 comes from adding 1 and 2. This 3 comes from adding 1 and 2. So then what goes here is, well, 3 plus 3, or 6. And then once I hit that middle point of Pascal's triangle, the numbers reflect back. So 3 plus 1 is 4, and then 1. So the coefficients of this part of the expansion here are 4, 6, 4, and then 1. So if you know the pattern in the exponents and you can figure out various rows of Pascal's triangle, then you can figure out the expansion without actually multiplying it out. And having multiplied stuff like this out all year, that's actually super sweet that you don't have to actually do the multiplication. So if I wanted to know what a plus b to the 5th was, then I just have to find the next row of Pascal's triangle. It's 1 and then 5. And then 4 and 6 is 10, 4 and 6 is 10, 4 and 1 is 5, and then a 1. Those are all my coefficients, and then I just have to put the exponents in. So a plus b to the 5th power is a to the 5th, plus 5, a to the 4th b. Remember, the a's are going to go down, an exponent, plus 10 a cubed b squared, plus 10 a squared b cubed, plus 5 a cubed, a b cubed, and then plus b to the 4th, and then plus b to the 5th. Made a little boo-boo there, sorry. That's supposed to be a 1, and that's supposed to be a 4. And so then this is that number, or is that binomial all expanded out. Now, if I were to ask you for a plus b to the 20th power, well, having to find the 20th row of Pascal's triangle, no matter how easy it is still rather tedious. So I want a better way to do this. Is there an easier way to generate the coefficients, or a more efficient way? And of course there is. I wouldn't be talking about it if there wasn't a way to do so. But before we do that, I want to show you what to do when you don't have an a and a b, you have different expressions in there. So for example, if I want to use this information to figure out what 2x minus 3 to the third power is, I'm going to do a substitution. I'm going to say a equals 2x and b equals negative 3, and it's important that you take the sign with that. And then I'm just going to write out what the expansion is for a and b. I have a cubed plus 3a squared b plus 3ab squared plus b cubed. And then what I'm going to do is substitute in the a's and the b. So a is 2x, so I have 2x cubed plus 3 times 2x squared times negative 3 plus 3 times 2x times negative 3 squared, and then plus negative 3 cubed. And if I multiply these all out, then I'm going to get 2x minus 3 cubed. And that is how you can use the patterns in the expansion to multiply out any old binomial. So what we want is to figure out the pattern in generating the coefficients without having to draw the triangle. So I'm going to start by treating this like just a sequence of numbers and thinking about what I have to do to the previous number to get the next number. And I'm going to start with 6 and 15. Now, I could say add 9, but it's not add 9. In order to get 15, I take 6 and I divide it by 2 to get 3, and then I multiply it by 5. And then in order to get the 20 from the 15, well, if I take 15 and I divide it by 3, I get 5, and I multiply it by 4, I get 20. You might see something going on here. Well, to get 15, what I do is I undo what I did to the 20. So I just have to multiply by the reciprocal of 4/3, which is 3/4. And then to get 6, I do the same thing. I multiply by 2/5. And I'm kind of running out of space, so 6 times 5 times 4 times 3 times 2, over 2 times 3 times 4 times 5. And if I want to retroactively go back and add in the 1 times, I can do that. And go back in, this is 6 over 1, and add the dot, dot, dots, let's say that goes on. I want a different way of thinking about this as opposed to having to write all those numbers out. I want something more compact. And the thing that I'm going to use, of course, is the factorial. So I'm going to write these in factorial notation, and what I need you to look for is the pattern in the factorial notation, because if you can see that, then you can generate any term of Pascal's triangle. All right, so let's start here again, okay? So and let's look at the numerator. It's like I started off with 6 factorial, but I chopped off the 4 times 3 times 2 times 1. All right, so on the numerator, I want to start with 6 factorial. And remember, if I divide by a factorial, the stuff cancels out, right? And so if I divide by 4 factorial, which is 4 times 3 times 2 times 1, then what I get is 6 times 5. But then I had 1 times 2, and 1 times 2 is just 2 factorial. All right, so then if I look at this one, in the numerator, I have 6 factorial, but I chopped off 3 times 2 times 1, which is 3 factorial. So I divide off 3 factorial, and then what I add on, 1 times 2 times 3, is 3 factorial. And so if I look over here, on the numerator, I have 6 factorial, but I chop off the 2 and the 1, which is 2 factorial, and I add on 1 times 2 times 3 times 4, which is 4 factorial. And then if I look at this next term, 6 factorial, the only thing I chopped off was the 1 factorial, and I have 1 times 2 times 3 times 4 times 5, which is 5 factorial. Now, I have enough now to figure out the pattern. Well, the numerators for all of them in row 6 are 6 factorial. And this first number I'm dividing by decreases by 1, so that means it would have to be 5 factorial here, and it would have to be 6 factorial there. And it would have to be 0 factorial there. And remember, when we defined factorial, we said 0 factorial was 1, so you can have a 0 factorial. And this second number increases starting from 0, and it goes all the way up to 6 factorial. And this is how you generate each of the terms in row 6 of Pascal's triangle. So using this information, if I know I want the coefficients for, say, row 9, or the coefficients for a plus b raised to the 9th power, the very first number in the triangle is going to be generated by 9 factorial divided by 9 factorial 0 factorial. And then the second number in the row is going to be 9 factorial over 8 factorial 1 factorial. And the third number in the row is 9 factorial over 7 factorial 2 factorial. And then the fourth number in the row is 9 factorial, 6 factorial, 3 factorial. Now you notice in the bottom, they always add up to the 9 that I need, right? But you'll also notice that this number here is one fewer than the number of the term I want. So if I want the 5th term, I'd have to have a 4 factorial there, and then 4 plus this number has to equal 9. So having looked at row 9, I think we can now jump to row n. So if I look at the first term of row n, I'm going to have an n factorial in the numerator, and then I'm going to divide it by n factorial 0 factorial. If I look at the second term, it's going to be n factorial, n minus 1 factorial, 1 factorial. If I look at 3, n factorial on top, n minus 2 factorial, 2 factorial. So you can see that I'm decreasing 1 on that number, and I'm adding 1 on that number, which lends itself nicely to factorial notation. Now if I want to scooch to the kth term, right, I have n factorial over, and then the kth term is not, it's not going to be n minus k, because the second term was n minus 1, the third term was n minus 2, so it's going to be 1 less, so it's n minus k minus 1 factorial, so it's 1 fewer than k, right? And this is going to be k minus 1 factorial. Now that is not pleasant to write at all, so instead of thinking of it as the kth term, you can also make this look nicer by saying the k plus 1 term of a plus b to the nth power by just shifting it, because that minus 1 is annoying. So if I want to find the k plus 1th term of a plus b to the nth power, or the coefficient, I should say, coefficient, then it's going to be n factorial on top. That's not different. But since I define it as the k plus 1 term, then I can just say n minus k because it's 1 fewer, right? And then have factorial and then k factorial. So this is the way you normally see the rule to generate the coefficients of the binomial expansion or the entries of Pascal's triangle. And so of course, we can write this in sigma notation, and we can actually therefore write this binomial expansion in sigma notation, because this is the coefficient. So let's write the rule for the term first. So for the k plus 1 term of a plus b to the nth power, the coefficient is n factorial, n minus k factorial, and the powers of a and b, a to the n minus k, b to the kth power. Now that I have the expression or rule to generate a single term, now I can generate the entire expansion using the sigma notation by saying that a plus b to the nth power can be generated by the summation of k equals 0, starting with 0, you have to start with 0, to n factorial over n minus k factorial, a to the n minus k, b to the k. And so then this is the single squished together formula to generate any expansion.